Ina rau rangatira mā, ina iwi o tamoto, nona hau e whā, tēnā aku mihi mahana ki a tātou. Kei te whakamihi au, ki ngā mema o te aparangi mo tōku potitanga hei ahari mi te haere mai i tēnei rā. Kei te parangi au, ki te whakamihi ngā ahare ho au te aparangi. Tēnā koutou, tēnā tātou katoa. Ko wai au, ko taputai, tōku maanga, ko tangaruhe, te awa, ko porongahau takatai te whenua tupu au, ki te noho tamaki makarau, me taku mahi I Waipapa Tamata Rau. Ko Charles Clifton toko ingoa, no rewa kina tēnā koutou katoa. My Bachelor of Engineering years were from 1974 to 77 at the University of Canterbury, followed by my Master of Engineering years. When I started at Canterbury, we did not have calculators. All our calculations were done using engineering slide rules. I was fortunate to be taught the latest in reinforced concrete design by the late great Professors Bob Park and Tom Paulet, both Fellows of the Royal Society, followed by my Master of Engineering with Peter Moss. This made me very comfortable with reinforced concrete. I left university with a strong desire to design iconic reinforced concrete buildings. I got my wish to design those in London, doing the structural design for the headquarters of the Arab National Bank and the very spectacular King Saud University entrance gate in Riyadh. That is still the most spectacular building I have ever designed the structure for. In 1983 June, with a classic New Zealand reinforced concrete education, I walked into the offices of the Heavy Engineering Research Association to commence my job as HERA structural engineer. My job description was to build the technical foundation to grow the market share for steel, with a focus on multi-storey buildings. With structural steel now one of the most used building materials in New Zealand, it's hard to imagine just how different it was when I started at HERA. A major dispute between the Boilermakers Union and the government in the early 70s had killed off steel frame buildings. By 1983, the belief was that steel wasn't as good as concrete in earthquake. It was unreliable outside because it rusts. Unless it was encased in concrete, it would collapse in a fire, and besides, it would have union problems during construction. Investigating those claims, coming up with solutions and helping build the industry was how I would spend the next 25 years of my career at HERA. This started off with my first external supervision of Greg McRae at Canterbury, who developed some key outcomes for seismic design that were implemented into new buildings from 1990 onwards. The next big development was producing seismic design procedures for the three common forms of steel-framed seismic systems shown on the slide. This has been the foundation for steel seismic design since 1994. All these systems have performed very well in the spate of severe earthquakes we've had from then on. Traditional moment-resisting frames, which are beams to columns, have rigid connections, and that's always been the case. However, damage to those in an earthquake in 1994 in Los Angeles caused the connections to partially fail, making them the weakest link in the building. The buildings performed well. I saw the impact of this damage as a significant opportunity to put forward semi-rigid connections where the deformation occurs deliberately in the connection. In engineering terms, this was blue sky going well against conventional wisdom. I started this research in 1995, and it's led to the development of the flange bolted joint, the sliding hinge joint, and the optimised sliding hinge joint, which are shown on the slide. Including in one of the major buildings in the university. When I was presented with my PhD in 2006, the VC, the late Stuart McCutcheon, said those joints had better work, and they do. 1990, A severe fire in a steel frame building under construction in London subjected 2 stories of uninsulated steelwork to temperatures well in excess of 550 degrees, which was the temperature at which steel was considered to collapse. According to conventional wisdom, the building didn't collapse, damaged members were cut out and replaced and the building restored. Question then asked, why didn't it collapse? The only real way to answer that was to build a full-scale building and effectively try and burn it down, which was what was done in 1997 to 2003 in a test building in the UK. These showed that the composite floors had very high fire resistance. From 2000 onwards, I worked with the principal investigator for the UK tests and others to incorporate this reserve of strength into a design method which is now widely used in New Zealand, increasingly in Australia and the USA. And now that's the end of my time at HERA, and here are some of my highlights from the HERA years. I finished in December 2007, starting in University of Auckland in late January 2008 as Associate Professor. First time ever in the university. Looking back and looking at my academic credentials, I realised this was a very generous starting point offered by the university into academic life. One of the things I have pushed very, very hard is to establish the link, or to get students to establish the link between the physical nature of the material and the complexity of the mathematics. And to this effect, I have led the production of a range of world-first scaled teaching tools where you can demonstrate the behaviour of steel using rubber beams in the laboratory environment. Now I come to 4 defining moments in my career. The first of these was participating in the New Zealand Earthquake Society reconnaissance trip early February 95 to visit Kobe, which had been severely damaged by the Great Hanshin earthquake on the 17th of January with over 5,500 people killed. The earthquake caused extensive damage to a wide range of steel structures, including some modern systems, showed both the resilience of steel, but that it's not a miracle material and critical weaknesses can and will lead to collapse. For me, there are 2 abiding memories, just how quickly and brutally a serious earthquake can destroy our built environment in an advanced modern country, and secondly, the calmness and fortitude the population showed in the face of the disaster. Both of these were to be brought home with much more emotional impact in 2011 in Christchurch. September 2001, here were 3 iconic steel frame buildings that had collapsed at least in part due to fire. And from September the 13th, 2 days after, I was being asked at HERA, just how vulnerable are these buildings we're designing to fire? I realised that I had to very quickly understand the construction of the 2 towers, the influence of the impact of the planes, and try and explain as best I could to the profession the collapse sequence of Tower 1 and Tower 2. I published an initial paper on this through HERA to the profession a week after the attacks. Reports from subsequent detailed investigations over the following years showed my conclusions were almost 100% correct. And through this work, I got 2 additional sets of information that had very restricted distribution. 2 pictures from the animation of the plane going into the building are shown in the slide. The 2 arrows show the office where the closest person who survived the impact of the plane on the floor above them was located. In 22nd of February 2011, Jason Ingham, the late Professor McPender and I were in the Holiday Inn building in Cashel Street, Christchurch, presenting a seminar on the assessment and retrofit of buildings for earthquake. I was setting up the afternoon presentation when the room started shaking, gently for a second or so and then extremely violently. I clung to the speaker's console, lined up the neighbouring 14-storey Westpac building against the window frame and watched it move 1.5 metres from side to side. This is something you draw to illustrate the students, but you never expect to see happening in real life. The shaking stopped and we evacuated the building. When we were walking down Manchester Street, around rubble from collapsed buildings and pulling our overnight bags behind us, I thought of Linda's beloved dad, my wife Linda's beloved dad, as a school kid in Napier in 1931, walking home from school after the Napier earthquake, dragging his badly damaged bike, thinking sometimes history does repeat. When I was at the University of Canterbury in the 1970s, everything was concrete focused and Christchurch didn't get earthquakes. If someone had told me then, in the future Christchurch would be destroyed by a major earthquake, rebuilt in structural steel, and I would play a key role in that, I would have said no way. It goes to show you can't predict the future. October 2019, we had a call from our daughter, we were in Italy at the time, to say there was a huge fire underway at the New Zealand International Convention Centre in Auckland. I'd previously given fire engineering advice on this and knew the building well. As the fire burnt on, reports appeared in the press the building was about to collapse. I knew it wasn't and conveyed this to the press online from our apartment in Fasciano. The main structure performed very well. I was engaged as the expert advisor to the Fletcher Construction Company for what was one of the most complex and detailed post-fire evaluations undertaken worldwide, which retained over 96% of the total steelwork. Here are some of my career highlights from the time at University of Auckland. They have a common theme relating to my role in developing the use of structural steel and with this the development of safer and more effective buildings. Now to family. I first met my beloved wife Linda of 46 years in late March 1975, and our love story would have got off to a faster start if I hadn't been chased away by her landlady with a broom the first time I tried to ask her out. 2 became 3 when Emma was born in June 1985, and our wonderful daughter with her irrepressibly cheery nature came into our lives. At the beginning of 2019, our Em met Shahab, one of my previous PhD students, love at first meeting, and they got married in a wonderful ceremony complete with COVID-19 QR code a day before we went into lockdown in Auckland. Then our family extended again when their son Zubin was born. So, I come to the last slide. People and organisations that have been key to my career, and there are a lot of them. So, family first. Linda Eames, Shahab Zubin. My colleagues in the Department of Civil and Environmental Engineering for being so collegial and supportive. All my students, past and present. The late John Butterworth, who had a key role in my appointment at the University of Auckland, my colleagues from HERA and SCNZ, colleagues from University of Canterbury, especially the late Bob Park, the late Tom Paulet, and the very much alive, hopefully still, Greg McRae, and the late Gavin Fletcher, who appointed me at HERA in 1983, and apologies to anyone I have missed out. It's a huge honour to have been elected to Fellow of the Royal Society of New Zealand. Thank you all for being at my new Fellows presentation.
Thanks very much, Charles. That was fantastic. I don't think, do we do questions? I've forgotten. Why don't we have, because you've got like a minute. Do you want to come up and take a question or two? Does anyone have a question? No question?
Somebody must have a question.
What happens to the steel at 500 degrees?
Traditionally, steel resistance in fire is determined when you put a piece of steel in a thing called a standard fire test. And everything is defined, the furnace, the way you place the steel. When you heat it up, turn the fire on, it gets to what is the defined point of failure, which is a deflection at 550 degrees, and that's become known as the failure temperature for steel. The thing is, it bears absolutely no resemblance whatsoever to happens to steel when it's in a building. So it's a defined failure temperature that has no bearing on reality.